Hi, Assalamualaikum and very good morning. My name is Nurin Ameyrah Aifaa binti Wan Dzlyshah, and today I will be presenting my thesis entitled Intelligent Data Interpretation for GPR Supported Monitoring of Underground Water Pipeline Leakage. This work was supervised by Surveyor Norzaliani Ghazali and Dr. Mimidiana Ghazali. My presentation will cover 6 main parts, which is the introduction and end with the references. So, background of study, there is an opinion that says underground water leakage are difficult to detect because they occur below the surface and cannot be identified through visual inspection. As we can see, first supporting study states that traditional detection methods are time-consuming and depends heavily on environmental conditions, often producing noise disturbance. GPR, however, provides subsurface imaging and manual interpretation is prone to human error as highlighted by Jiang et al. 2025. The main problem in underground leak detection is that current methods are reactive and radiogram analysis is inconsistent. Reactive detection means leaks are usually found only after damage has already occurred, such as road subsidence, or which makes repairs more costly and unsafe. At the same time, interpreting GPR radiogram depends heavily on human judgment, misleading to an error. Why is this study important? It is because proactive detection can prevent damage before it happens. This means safer infrastructure, lower repair costs, and reduced non-revenue water losses. In Malaysia, where water management is critical, this kind of proactive systems can make a big difference. The aim of this study is to apply CNN to optimize GPR data interpretation. My research questions are: how can deep learning interpret the GPR signals consistently and reduce human error? And how can CNN achieve the best performance in detecting leaks? To answer this, I developed a CNN classification model and evaluate its performance using accuracy, precision, recall, and F1 score. Next, water distribution systems are complex networks, and the literature shows that integrating AI can improve their efficiency. This connects directly to the issue of water leakage, where joint failures change soil moisture, creating signals that can be detected. To capture those signals, surveyors use GPR to subsurface imaging, but leaks blurs radiogram, making manual interpretation difficult. Finally, the literature highlights the risk of undetected leaks such as erosion and sinkhole. Altogether, the review shows that combining GPR with CNN is a promising solution to improve proactive leak detection. Okay, for the method, first phase is the definition of study. In this phase, I define the project scope, review the literature, and select the study area. The chosen sites were UiTM Arau and Taman Seri Wang, which provide real condition for data collection and comparison between different pipe materials. For the second phase, however, is where the data was gathered both on-site and through simulation. At UiTM Arau, HDPE pipes were studied, while at Taman Seri Wang is to get metal pipes data. Simulated diagrams were generated using GPR sim, and additional datasets were sourced from Kaggle, GitHub, and ResearchGate to strengthen the datasets. Then the raw GPR data was cleaned through time zero correction and gain adjustment. After pre-processing, the data was fed into the CNN model for training and testing, allowing the AI to learn leakage patterns across HDPE and metal pipes. The last step is the execution of CNN. Finally, the CNN models was executed and its performance compared through categories. Precision, recalls, and F1 score were measured to evaluate how well the model detected leaks in both UiT Ameyrah and Taman Seri Wang. Okay, for the result, it shows that the CNN model trained through transfer learning achieved stable and consistent learning performance. The training and validation curves both increased steadily, reaching around 0.9. This indicates that the model successfully learned the underlying patterns in the GPR data. However, the confusion matrix provides a deeper look into how the model classified each pipe condition. The highest correct prediction occurred in metal with water and HDPE with water categories, showing that the model was most confident when water leakage was present. This is because the training datasets for water leakage was larger and clearer, allowing for CNN to learn strong leakage features. However, the model struggled with dry pipes. This imbalance reflects the data quality rather than physical detectability. In real-world GPR interpretation, dry pipes are easier to identify because they produce sharper hyperbolic reflection, but in this study, the CNN's performance was limited by fewer samples during training. So for the conclusion, even though my data was not fully accurate, I have successfully achieved my research objectives and demonstrated that the model can detect water leakage using GPR and CNN with promising result. The main limitation of this study was the dataset imbalance, where water leakage samples were stronger and more representative than dry pipe sample. These are all the list of references that I have been using.